What up, Algebra Squad? All right, this is a 6.1 lesson. It's titled Solving Systems of Equations by Graphing. Now, let's break down this title so we understand what it is that we're talking about. This right here is going to be the new part. All right, I'm going to box it in. What is a system, right? What is a system? We already know that equations have an equal sign. And now we know that graphing would include the coordinate plane, right? For the most part, if we have x's and y's, which it will. All right, so the equations that we're talking about are lines. We are going to be talking about linear equations, just lines, okay? Now, this should be simple because, let me fix my little equal sign. We just finished a lesson on linear inequalities where we graphed lines and then we decided whether the lines were either, I'm doing this so I can suggest either dashed or solid, right? And then we decided whether it was shaded above or under, right? So we already know how to graph lines. Now, we're not going to do inequalities. These are equations. Equations have the equal to. So the lines that we're going to be using are going to be all solid, and there's going to be no shading. There is no shading right now, okay? Later on, we will talk about systems of linear inequalities. So what does the word systems mean? Systems just means more than one. We are going to be dealing with more than one line. Ta-da! That's it. That's all there is to it. More than one line. Now, what is it that we're going to be looking for? Well, we're going to be graphing them. And what happens when we graph them is we are going to decide what the solution is, okay? Because we always have to find some sort of solution, right? This is math. We're finding some sort of solution. Now, when you have only one line, there is an equation, right? There's an equation. Let's say I'm just going to make a random one up. Y equals 2x plus 7, okay? Which does not go with this line because we have a positive slope. The slope is 2. Okay, so what this means is, anything that makes any point that is on this line, right? A line is made up of infinite amount of points. Any coordinate that you decide to grab from this line, let's say we grab this little point right there, and that point is, I don't know, I'm just going to come up with random numbers. Let's say 6, 12, all right? Well, since this point is on this line, if I were to grab my 12, which is y, and put it in here, and grab the x, which is 6, and plug it in there, when I solve this, this should be true. It should give me a true statement. It should say something like, let's just make something up. 12 equals 12. Obviously, you can do the math and see that this might be incorrect, but whatever. I'm not about to do that right now. So the solution to one line is all the points that are on that line. 1 second, I'm going to say it one more time. The solution to a single line are all the points, all the x's and y's that make that line. Because if I grab any of those points and I put them into the equation will be true. Now, but let's not forget, what happens when we have more than one line? What is the solution there? Well, when we have more than one line, say this green line right here, which all the points that make up that green line are the solution to that line. And let's say this blue line, what is the solution there? Well, let's talk about it one more time. The solutions for the green line are all the points, which are an infinite amount of points, infinite. I will keep reminding you guys that because this line goes forever. It extends forever. So all these points that make up this green line are the solutions to only that green line. Only that green line. Did you guys hear me? I said only that green line. Don't forget, only for that green line. The solutions for the blue line are the points that only make up that blue line. So if the point is on the blue line, it's only the solution for the blue line. What do you guys think is the solution for the system? For the more than one? Can you guess it? Can you guess it? Can you guess it? There it is. The solution for a system of equations is where the lines cross. Why? Because that one point is located on both lines. Crazy, right? Insane. Well, that's how we're doing today. So let's get on it. Now, before we get on with the actual practice, we have some terms to learn, all right? Some terminology. So go ahead and use that paper, that top portion that I gave you guys some space to make up your notes here. Now, consistent and inconsistent systems, all right? We got two words to talk about. We have consistent and inconsistent. All right. What do you guys notice? What do you guys notice about these three diagrams? on the farther left and the further left side, right, we have two lines that are crossing. We have a point of intersection. Beep. In the middle, we have two lines that are overlapping. Now, you might look at it and say, they're not overlapping perfectly because I could see some blue still sticking out. Well, we have to make that visual so you know that there's two lines that are overlapping. They're perfectly overlapping each other, okay? And then on the right side, we have two lines that are parallel. They will never intersect. Look at the difference between what makes something consistent and inconsistent. This one is consistent. Don't worry about the word independent or dependent. This one is also consistent. Why do you think the first two on the left side are consistent while the one on the right side is inconsistent? Think about that for a second. See if you can generate some sort of idea on that. Okay, so the idea is that if we have a point or points that these two lines share, we have a consistent system. Now, if you look over here, we do have a point that we share. We have a single point. We have one solution. That's what makes it consistent, okay? Notice that here we have infinite solutions. That's what makes it consistent because we still have solutions. We have solutions here, a single solution, and we have multiple solutions here. To be more accurate, infinite amount of solutions. Why do we call that infinite amount of solutions? Because if I were to ask you, where do these two lines intersect? You should say, well, Mr. C, that's a silly question because these lines don't really intersect at a single point. These lines are overlapping. They make essentially the same line. Therefore, every single point, which is infinite of them, that they have, one line has, then the other line also has. That's why we have infinite solutions, okay? And then here on the right side, we have something that's inconsistent. In is the prefix of not, okay? Inconsistent. That will tell you that we have no solution. No solution. Why is there no solution? Because these two lines will never meet. Oh, that's so sad because I feel like they're meant for each other, but they'll never meet. You like my corny joke? These lines never meet. These are parallel lines that will never intersect. Therefore, there's no solution. Inconsistent. Okay, no answer. Parallel lines. All right, that's the terminology. These are the three ideas that can possibly happen. Okay, three ideas that can happen. You can either intersect once, intersect infinite amount of times, or intersect no times. All right, example number one. Let's go ahead and see what it is that we want to do here. Use the graph to determine the number of solutions the system has. All right, check it out. We have the first thing that they're asking us. Then state whether the system is consistent or inconsistent, and if it's dependent or independent. Woo! Dependent or independent. We'll talk about that in a second, okay? So that's also new. All right, the first thing we want to do is obviously graph these two so we can see what it is that it looks like. We're going to go ahead and start with, I'm going to call this the red line. It starts with the y-intercept of 1. So I'm going to go to my y-intercept and put a 1, which is located right there. And I can see that my slope is on -3. Remember that when your slope is a whole number, you put a 1 under it, and that's going to be your rise over run. So -3, 1. So if I decided to go up 3, then that means I need to go to the left 1. Again, I'll go up 1, 2, 3 to the left 1, 1, 2, 3 to the left 1. I can also go down 3, 1, 2, 3 to the right 1, down 3 to the right 1. And this is the staircase pattern that I'm generating with a rise over run of -3. Now, if you look at my line from left to right, you should notice that my line is a negative line. I'm just making sure I create my line here properly. No. Come on now. Give me my line maker. All right, there we go. Okay. So we have that line right there. And let's go ahead and create the other one. We have a y-intercept of -3. So we go to -3 and we create a point right here. And then we have to follow the ladder of 1. So my slope of the blue one is 1. So up 1 to the right 1, up 1 to the right 1, up 1 to the right 1. And you can see that this is going to be a never-ending diagonal pattern here. Okay. Let me just, might as well. I already started it, right? And now let's make the line. Here it is. Okay, guys. So the first thing, let's go look at A, part A. Use the graph to determine the number of solutions that the system has. Well, how many systems do we have here? How many solutions do we have here? One solution. We have one single solution where the lines intersect. One point. That's your solution. So we have one solution. And it's always good to state where that solution is located. That solution is located 1 to the right and then down 2. So it's 1 comma -2. That's my solution. B, states whether the system of equations is consistent or inconsistent. Well, guys, we generated a solution. So that means consistent. Actually, let me go back really quick and see if, oh yeah, the words were there. Sorry, I didn't talk about these, but I'll bring it to you guys in a second. Or maybe already. So I'll refer to it right now. Okay, so now the question is this consistent independent or is it consistent independent? Well, just think about these two lines. Are these lines unique? Are they independent, meaning like I got my own style, I got my own slope and my own y-intercept? Are they unique or are they identical, right? Think about it that way. Well, when you have two lines like this red line right here and this blue line right here, that they're kind of unique. They're their own line. They don't follow each other's slope and y-intercept. We're going to call them independent. I'm an independent person. I'm unique. I got my own style. All right. I don't know. That's the way my mind thinks of it. And then dependent, you're kind of, you're depending on the other line to look like exactly like the other line, right? So that would be a good way of thinking about this idea. All right. Where your X's and Y's, they are dependent on the same, on the other lines, X's and Y's, they're identical, right? Here we got two different lines. So we have independent, consistent system of equations that has one solution. All right, there we go. That right there, this little piece right here would be part C, I guess you can call it. Okay, part C. Actually, let's make it nice. Let's make it nice. If we're gonna do it nice. Okay, independent. That's it, guys. There's nothing else to it. Here's where your two lines will cross. That right there. And what does that mean? What does that mean right there? We've talked about, okay, cool, they cross there, but what else does that mean? That means that out of all the infinite amount of blue points, infinite, there's infinite amount of blue points, right? And out of all the infinite amount of red points, infinite. Think of the number infinity for a second. Let that simmer in. It's a number that you will never in your life, no matter how early you start counting, you will never reach it. We will all die before anybody will get to. It's impossible. It's kind of silly for me to say that. Out of all the infinite amount of red points and infinite amount of blue points, only 1 point, just one, will make the equation true for both. Look at this X value and look at this Y value. These are the only two numbers in the world that when you plug into the red one and the blue one, they will both work, okay? You can try that if you want. It'll work out. You plug in your X, 1 for your X and a -2 for your Y, solve it, and you can see that you're going to get true statements, okay? That's what it means to have a solution or to be the solution. All right. Part B. Here's part B. Same question, just part B. So let's go ahead and call this top one right here the red one, starting with a y-intercept of 2 and with a rise over run of 1, 2, up 1 to the right 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 2. So down 1 to the left 2, 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 down 1 to the left 2. Here are my reds. Let me just already do the dots for the blue one. We got -1 for my y-intercept and the same slope. Oh, what is that? What do you think that's gonna look like, y'all? Same slope, same tilt. The line tilts the same amount, right? Up 1 to the right 2, up 1 to the right 2, up 1 to the right 2. Maybe if I keep going, there's gonna be somewhere that they intersect, right? Do you think so? And the answer is no, silly goose. The answer is no. These two will not intersect at any point. When you have the same slope, that means you have the same tilt, the same steepness of the line, okay? They will never intersect. So how many solutions do we have? 0, no solutions. So sorry, let's not put 0. Let's put no solutions. Sounds a lot prettier. No solutions. And the reason why we have no solutions is because we have a system that is inconsistent. Inconsistent system. Okay? Inconsistent system. Right now, we don't need to say if it's independent or dependent because these are, check it out. These are parallel lines. So inconsistent means that's it. It's obvious that they are independent of each other. Okay. It goes with that. All right, now really quick, think about it for a second right here on the bottom left. I know you don't have it on your worksheet, but think about it. Let's get those brain cells moving for a second. How could you change the equations in part B so they form a consistent and dependent system? A consistent and dependent system. I need you to pause this video right now. And what would you do to this graph? What can you do? If you can do anything to this graph, what would you do to make it this and that? Pause the video, try it out, think about it. All right, let's talk about the answer here. Number 1, to be consistent, that means you have to have a solution, at least one. Solution needs to have solutions. Now, we have 2 options. There's either one solution where the lines cross like this, and they have one intersection point, or we have the overlapping. We have the red and we have the blue, and they essentially are the same line that they overlap and they have infinite solutions. So that is where we have to read right here. Are we talking about, when we say dependent, are we talking about one solution or infinite solutions? Dependent means they depend on each other, right? They depend on each other. They got no originality. They are the same exact line, same exact line. So we need to look at this. How can we make the red dots and the blue dots look like this? Well, it's very simple. You got 2 options. We can either grab the equation, the red equation, and move it down 1, 2, 3 units, right? We can either move it down 3 units by grabbing this number right here and subtracting 3 from it. Because think about it, what's 2 minus 3? It'll take you to -1, and now they will both be identical. Or the other option would be to go up, where we grab this number right here, this y-intercept, and we say, hey, y-intercept, I need you to go up 3 units. That's it. And then these 2 lines will be identical. They will be dependent, consistent dependent system of equations. Yeah, that was a lot. All right, guys, here it is. We have a check problem. Luckily, you do not have to graph it, but go ahead and practice your knowledge of the terminology. Go ahead. All right, so obviously here, they're asking you for, is it consistent or inconsistent? And then state the dependent or independent style. All right, here we go. So this first one right here, parallel lines on the left side, we have no solution. So this is inconsistent. This is inconsistent. We have 2 lines that will never meet because they have the same slope. And the most important thing, what makes them stand out and what makes them parallel and not the same line, remember from the practice problem that we did earlier, since these 2 numbers are different, that means that these 2 lines that are tilted the same way, they are parallel from each other. If you were to get these numbers to be the same, then we would have the same exact line or lines that overlap. Okay. Or think about it that these 2 lines have different heights. Okay. On the right side here, we have, obviously, we do have an answer. We have a solution that keeps our system consistent. We have a single solution here. These 2 lines are unique. You know, one's the blue line that's tilted a specific way, and it's got its own y-intercept of -1. So this would be consistent and independent, right? This is way too easy, right? All right, guys, here we go. Parallel lines. Just kind of read this through, put this information in your mind. 2 lines that have the same slope are parallel and never intersect. A system of parallel lines has no solution. That's probably like the 9th time I say this, but it doesn't hurt. All right, example number 2. I'm going to challenge you. Do it on your own. Pause this, try it on your own. All right, so this one is saying to determine the number of solutions that it has, and if it has one solution, determine the coordinate, okay? I'm going to go ahead and practice the same idea with the terminology that we learned before. So I'm going to go ahead and answer this question fully, encompassing everything that we talked about. All right, so I'm going to call this my red line equation, starting with a y-intercept of 14, and then a negative slope of -2. So that means I have to go down 2 to the right 1, down 2 to the right 1. And every tick mark that we see here is already 2. So I would have to go to the next tick mark right here, and then to the right 1. Once again, down 2 to the right 1, down 2 to the right 1, down 2 to the right 1, down 2 to the right 1. And then every time that I'm moving to the right, I'm actually going halfway because I need to go only 1 and not 2. The concentration when I do this is real. I'm trying to not mess it up. All right, what does this one look like? We have a y-intercept of 1, so I'm going to go ahead and put my first dot on 1 on the y-axis, and then 3 over 5 up 1, 2, 3 over 1, 2, 3, 4, 5. There you are. And then I'll do another 3 up 1, 2, 3 to the right. 1, 2, 3, 4, 5. You know, let me make one going down. 1, 2, 3 to the right, left. 1, 2, 3, 4, 5. And let's do another one just because my OCD. 1, 2, 3, 1, 2, 3, 4, 5. Cool. All right, we got it. Let's make this thing. Here we go. So we got the red one. Oh no. Come on, give me the line tool. Okay. Got that one here. There we go. All right, cool. Got it. All right, guys. So our solution is right here. This is a consistent system. So I'm going to go ahead and say right here that this is oh my land. Consistent. It's a consistent system that has independent lines. Okay, independent lines. They got their own thing. And they do have one solution. So one solution. The one solution is located at 5. This is 5, and then up 4. This right here is 4. So it's 5, 4. Cool. Easy peasy lemon squeezy. All right, here you guys have your check problem. Try it out. Pause the video. Do not cheat yourself. All right, so let's go ahead and check our answer here. As always, I'm going to do this as the red one. Now, what do you think has to happen here? Well, for us to put this in graphable form, we want to turn this into slope-intercept form. Slope-intercept form means we want to get our variable y by itself by taking the 3x to the other side first. Inverse operation subtraction. All right. Now we have 5y is equal to negative 3x plus 10. The 3 and the x do not combine. I'm sorry, the 3 and the 10. They are not like terms. If the 10 happens to have an x, then yes, you can combine them, but it does not. So you have to leave them separate. Now we take the 5 to the other side by doing division. Don't forget to do the division on all the parts of the equation. All the parts of the equation. Negative 3 over 5 does not simplify. So just leave it as negative 3 over 5. That's it. Don't get scared of this fraction. That's your rise over run. It tells you how much you go up or down and then left and right. Keep your variable next to it, and then 10 divided by 5 is 2. Simple, 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 simple. That is right there is going to be our red equation, which has a y-intercept of 2 and then a negative slope of 3 over 5. So I'm going to go down 3 so I can just not make a mistake with my negative line. 1, 2, 3 to the right. 1, 2, 3, 4, 5. Down 1, 2, 3. 1, 2, 3, 4, 5. I'll go up 3. 1, 2, 3. 1, 2, 3, 4, 5. And I'll stop there just so I can work on the blue one now. All right, so we got the blue one here where you can see that we need to do the same exact thing. The blue one says x minus 5y equals to negative 10, where we will do the same exact thing here. We'll take the x to the other side by subtraction because the x is positive. I know that right here, a lot of students get confused and they want to take the x by adding because they see that Hey, why doesn't it erase my arrow? Okay. They see that subtraction there from that -5, but that belongs to the -5. So do not think that, that our x is negative. Our x is now going to the other side, keeping our -5y here. The negative or minus x still needs to be applied. And then the -10 that did not or is not able to combine with the x because they're not like terms. They don't have the same variable. So don't do anything. Here you need to understand that the -5 and y are multiplying. They are multiplying. So the opposite of multiplication would be to divide. That is how we take the -5 to the other side. Don't forget to divide everything else, every other part of the equation by that same value. That is now going to give me -5 divided by -5 is the same thing as 1 or 1y. And now we have a negative divided by a negative. These negatives right here will undo each other because a negative divided by a negative is a positive. And then the next thing I want to remind you is that always and forever, if you don't see a number in front of a variable, always think about it or see it as a 1. So that is going to leave us with a positive 1/5. Remember, the negatives canceled out. Then keep the x next to our fraction here or whatever coefficient we have. Once again, a negative divided by a negative will give us a positive. Positive is going to give us, it's going to prompt us to be addition. And then 10 divided by 5 is 2. All right. What do we notice here? We notice that we have the same, right? We have a 2 here and a 2 here. That's kind of like where my brain went to. And I thought, oh, wow, we might have the same exact line. But we don't. We have actually, we already know where they're going to intersect. We should, because look, they intersect right here. We have the same y-intercept. And then what happens after this is we have a negative slope of this one of, I'm sorry, a positive slope of 1 and 5. So up 1, 1, 2, 3, 4, 5. Up 1, 1, 2, 3, 4, 5. I can go down 1, 1, 2, 3, 4, 5. And I'll leave it there. I don't need to do anymore. Make my line. Good enough. Whoa. Okay. There we go. It's very evident what the answer is. The answer is 0, 2. They intersect at 0, 2. What type of system is this? This has a solution, so it's considered to be consistent. Now, how many solutions do we have? Since we only have one solution, it is independent. These lines are independent of each other, right? They don't rely on each other. Okay. And then the last thing would be consistent, independent, the solution. Never mind. We got it all. We got everything. That's it. Example number 3, and I believe this is the last one. Pause it and try it now. All right, let's go ahead and start with the -3x plus 2y equals 12. Here, we're going to be taking the 3x to the other side by addition because I could see that that 3x is negative. So by adding it, it'll cancel out. Not only will it cancel out from the left side, but we'll then take it to the right side, which is exactly where I want it. If I want to put this in a graphable format. My last step here is to take the 2 to the other side. Remember that the operation that's happening here is multiplication, and the inverse is to divide. A 2 divided by 2 is 1, so it kind of just goes away, which is exactly what I want. We want the y value to be by itself. Here it is. 3 divided by 2 cannot be simplified, so just leave it as 3/2 or 3/2. Keep your x next to that fraction. That way you can just see it as a fraction by itself, and then 12 divided by 2 is 6. Cool. Done here. The line that this will create would be an y-intercept of 6 and then a rise of a run of 3/2. So if I go up 3, 1, 2, 3 to the right, 1, 2, I'll be here. 1, 2, wait, 1, 2, 3 to the right, 1, 2, right there. Down 3, 1, 2, 3 to the left, 1, 2, right here. I'll stop there. I don't have to do that many more because I'm running out of breath. All right, next question. So the next one here is 6x minus 4y equals 8. I will be taking 6x to the other side by subtraction. Why subtraction, Mr. C? Because we shouldn't be adding because I already see a minus right there. No, because the 6 is a positive 6. The only way that you can take 6 away from 6 is by doing 6 minus 6. Now we're left with -4y. Don't forget to bring that negative from the 4. And now here, the -6x and the 8 do not combine, so just leave them next to each other, like that. Our last step is to understand that there's multiplication here. So the inverse of multiplication is to divide. Remember, that's a -4. Take that negative with it. -4, -4. I'm doing this division to every single piece of the equation. We're now left with our final slope-intercept form of the equation, where you have 6 divided by 4. Let's start little by little. What's a negative divided by a negative? It's a positive. So get rid of the idea of a negative, okay? I don't want to put those X's there because it's going to get confusing. So get rid of the idea of a negative. That's it. No more negative. 6 over 4. How can you simplify 6 over 4? You can divide them both by 2. 6 divided by 2 is 3. 4 divided by 2 is 2. Cool. Apply your variable next to the coefficient. And now, a negative divided by a positive or a positive divided by a negative, it does not matter. Since we have one of the numbers negative in this division, it's going to keep a minus symbol on the next part of our equation. And then 8 divided by 4 will give us 2, -2. And here we go. So let's go ahead and start with a, a y-intercept of -2, which is located right here. And now before I continue, can you guys understand that we can see what the answer is? Before we even graph it, we should know, before we even graph this, we should know what the solution is. We should know the answer to this question. Guys, we're about to graph 2 lines that have the same tilt. They are tilted the exact same way. What does that mean, Mr. C? Can you please elaborate? Look at this line that I made right here in green. I'm about to clone this line. I'm going to clone it. Now I have 2 lines that are tilted the exact same way. Now, notice that it doesn't matter where I put this other line. It doesn't matter. I can put it higher, lower, higher, lower, higher, lower. I can put it more to the right, more to the left. As long as these 2 lines have a different height. What do I mean by different heights? Well, if I bring this lower line to the same height as this one, I have the same exact line. That means infinite solutions, right? But if I change the height of it, meaning the y-intercept, and look, that's a different height than that one. So that means that these 2 lines are parallel. They have the same tilt, same exact slope, rate of change, but different heights. That makes them parallel. So we got parallel lines here. This is an inconsistent system with no solution, obviously. That's what it means to be inconsistent. I'm just going to still graph this. So 1, 2, 3 to the right 1, 1, 2, 3 to the right 1. Wait, it's not to the right 1. It's to the right 2. Careful. 1, 2, 3 to the right 2. 1, 2, 3 to the right 2. 1, 2, 3 to the right 2. All right. And we have it right here. I'm not going to make my perfect little lines. I saved some time here. Save you guys a little bit of a headache. And there we have it, guys. We are done with today's simple, very simple lesson. I hope that this was too easy for your brain. And just get ready for our practice problems coming up next. Peace out.